So this chapter is all about the atmosphere, its composition and structure, and how we observe it. So we'll start with that. Let's just look at what is the composition and structure of our atmosphere? Well, think about it. You don't think about dust being part of the atmosphere, but it is. And this is an example of dust coming from Africa over the tropical Atlantic, all the way into the Caribbean islands and even southeastern U.S. It happens periodically. These dust storms will develop over the Sahara and move towards the west and across the area. And they transport a lot of dust, and there's been times visibilities, for example, at San Juan, Puerto Rico, sometimes go down to a quarter mile in dust. And even at times they'll get into places like Charleston, South Carolina, Miami, Florida, and reduce visibility there. So this is one aspect of just looking at the atmosphere, that we have dust in it. And so what happens with our atmosphere? It changes quickly. You can be walking outside one time and it's beautiful, and the next there could be a tornado and causing all kind of damage. So the atmosphere is part of what we describe as the Earth's system. So the Earth's system consists of the atmosphere, which is what we're going to spend our time in. But every one of these interacts with each other. The hydrosphere is just water. So anything that deals with water on the surface, for example, oceans, lakes, ponds, uh, rivers, all of that is water. The geosphere is like the rocks, volcanoes, things like that. And they interact with the atmosphere as well and change it. The biosphere is us, or plants. So all of that comes together to form what we call the Earth systems. And in our case, what we're going to look at is the atmosphere. And you think about it, the atmosphere is really thin. Uh, Almost half of its mass is below 18,000 feet. And as a matter of fact, 99% of it is below 20 miles. Uh, so if you were running a marathon, you could run to the top of the atmosphere during that race. Now, it tells you how tiny the atmosphere really is. The bottom part of the atmosphere, most of the atmosphere, is what we have here, uh, homogeneous. So in other words, it's made up of nitrogen at 78%, oxygen at about 21%, argon about 1%, carbon dioxide. Even water vapor comes in here, as do other gases. But interestingly, that percentage that you see, if I was at the surface of the Earth, 78% would be nitrogen. If I was at the top of Mount Everest, 78% is still nitrogen. So that is an interesting fact with our atmosphere. That as you go up in the troposphere and even into the stratosphere, our atmosphere remains exactly the same proportions. And here's how many parts per volume and all the gas looks like. So there are also aerosols. I just showed you a picture of dust. I don't know if you don't remember, I am sure, back when smog used to be very prevalent, but it used to be around all over the place. And we've cleaned it up a lot through the years. But back then, that was another form of particles in the atmosphere. Wind, dust storms, puts dust in the atmosphere. Ocean sprays. Every time there's a wave breaks, the ocean gets sprayed out. Some of the ocean winds up in the atmosphere, some of the salt. Forest fires, even volcanoes. Water is a part of the atmosphere too. It's a significant part, actually. But by volume, it's less than 4%. And most of it is in the lowest 1 kilometer of the atmosphere. So really down low. Carbon dioxide, we need it for life, for photosynthesis. And we're going to talk about this a lot later. Both carbon dioxide and water vapor absorb and emit infrared radiation. And we're going to deal with that in a little while. Here we have other pollutants. But we just talked about a whole bunch of natural ones. There are unnatural ones, you would say, I guess, that are man-made, and these are part of it as well. So we study the atmosphere by using what we call the scientific method. Almost every science class you ever took, and you may not have taken many, or you may miss this part, they all had what they call the scientific method. So let's look at that. I want to do it looking at a weather example. So I say I have a problem predicting thunderstorms that are over Virginia, especially when they come from the west. In other words, they develop over West Virginia and move across the Appalachian Mountains into Virginia. There are times when those thunderstorms will dissipate, and there are times when they get stronger. So the question that we ask, and this is actually a study that was done, University of North Carolina State University did the study for us, but there were several grad students they had, and the question we asked was why sometimes do thunderstorms dissipate when they move across the Appalachians, and other times the atmosphere looks very similar, but they keep moving right across and actually intensify. So we developed some hypotheses. We looked at things like moisture in the air, temperatures, how things, whether with upper atmosphere jet streaks, all different kind of things. We made a hypothesis that these different things we think contributed to that. And then we tested it. We looked at a whole bunch of cases and determined, well, do they or don't they? And some turned out didn't. So we went back and redrew it again. And eventually we got certain parameters that almost every time when they were in existence, thunderstorms that moved across the Appalachians would intensify. And if they weren't there, the thunderstorms would dissipate. So we were able to put this out and actually improve our forecasting. So what you can see is we were able to use the scientific method by asking questions, figuring out hypotheses, testing it, doing an analysis, and later coming up with results. The other ways we look at the atmosphere, we look at it conceptual models, graphical models, physical models, numerical models, all of those. Here's Purdue's tornado vortex chamber where they study tornadoes, for example, in a physical model. Numerical models. I worked on those when I was in grad school and used them numerously and even did some research with them when I was forecasting. But one key to every forecast that the Weather Service or anybody makes is we have to know what's going on now. Weather is what is happening now. We're not dealing with the weather forecast is what we're interested in, but currently what is happening now. So we wanted as much observations as possible. And one way that is done is automated surface observing systems, or ASOS. Almost every airport in the country has one of these. The reason they have it is because for aircraft to take off and land, they need to know what the weather is at that location. If they're going to take off, for example, they want to take off into the wind. If they want to land, they want to land into the wind. They don't want to land in a thunderstorm or fog. And temperatures actually impact how much runway they'll need to take off. All of those things are observed with this automated surface system. And they're observed every minute. So there's a continuous record every minute throughout the whole day. Another observing system that's out there is what we call the Cooperative Observer Network. These are stations, volunteers, they don't get paid, that are around the country. And what they do is put these weather stations in their backyard positioned, and they record precipitation, temperature. They're used for studying how much rain fell and how the climate looks because they're daily temperatures at these rural locations. And then you have COCORAS, which is a community of volunteers that measure all these same things. Basically, precipitation is really key on that one. Rainfall, hail, all of that, and you actually can find that on the web. So that is just the surface. Now we want to look at the atmosphere is 3 dimensions. Even though it doesn't go far, it is 3 dimensions. So we want to look at that. We look at that by using radiosondes. Radiosondes are the method. We tie them to the end of a balloon, a helium balloon, and they'll go up in the atmosphere gradually. We can predict exactly the speed that they'll go up, so we know how high they are. We can track where they've moved to. That's how much the wind is blowing them around. And as they're going up, we can take temperatures, dew points, and atmospheric pressures, so we can see all of that in the 3 dimensions. And eventually the balloon will get so big it breaks. And then there's a parachute on the instrument that'll open up and it can come to the ground. And ideally, that would come back to the ground and we would be able to recycle it and reuse that package. Almost all of them get lost, never make it. They may come back to the ground, but maybe a farmer finds it in his field and just tosses it in a trash can, whatever. Here's what the radiosonde looks like. Drop sondes are a radiosonde that's dropped out of an aircraft. Very simple. It's the only difference. Radiosondes go up with the morning sounding. Drop sondes come down from the All right, there was other things. Since we can't be everywhere in the atmosphere at one time, we use what we call remote sensing. Remote sensing means I'm looking at a part of the atmosphere that's not next to me. We use radars and satellites to do that. There are two mechanisms for remote sensing. The final part here a little bit is the atmosphere, we divide it by how the temperature changes. In other words, the troposphere, the temperature is decreasing with time, height. The stratosphere, it gradually warms. And the reason for that is ozone and how it's used to protect us. The mesosphere cools, and the thermosphere at the very top gradually warms. And up there in the ionosphere and the thermosphere, we actually have auroras that take effect. They are based on how much solar wind's out there, which develops the magnetosphere. And they can look like this, which are beautiful sights. I know for a fact, I got a picture from a friend in Ohio last summer where these came down into northern Ohio. And here you can see areas that are forecast to have these auroras, and they're based on how much solar wind is coming out from the sun. The National Weather Service, believe it or not, has an agency within it that's called Space Weather. They actually do this forecast. Here's another example, just looking at it through a satellite. So with that, let's go take a look at a couple remote sensing things. I wanted to start off with satellite. Easy enough. We can look at a visible satellite. This would be a satellite picture. If you were up in space looking down, this is what it would look like with your eyes. You would see these bright clouds here or over here where the sun's reflecting very well. Less clouds, all these are cumulus clouds, actually bubbly little clouds in here. More clouds down here, thunderstorms. And we can change this. I can say, oh, I don't want to look at that. I want to look at infrareds. Infrared is just a measure, different wavelength, and you can see the temperatures. So you can see colder temperatures in these clouds down here, pretty warm temperatures over the rest of the area. It's a way of looking 24 hours a day. Obviously, if you look down from space during the nighttime and we're just trying to see down there, you wouldn't be able to see. It's dark. So this way you're not having that issue. Another one of the things I wanted to look at, remote sensing, let's take a look at satellite. A radar, excuse me, here's radar. Look at all the reflectivity echoes. All we're doing is sending out a little pulse of microwave energy out that reflects back. The radars actually listen about 85 to 90% of the time for these pulses to come back. They send them out and then they listen. So that's how we're getting these reflectivity. The more intense the rainfall, the darker the reflectivity would be, the more yellows and reds. You'll notice a lot of the country doesn't have much in the way of precip right now. It's pretty dry. Finally, I just wanted to show you a radiosonde. This is a STUV diagram out of Minneapolis, Minnesota. I picked this one because there's the temperature curve going up. Here's the dew point going up. A little bit apart, but they get drier and drier as they go up a little bit more. So I would argue that there's some clouds up in this area, maybe not down in this area. Also have the wind here, and they're plotted according to pressure and height. You're learning and actually discussed a little bit about how warm air expands and cold air contracts, just like a lot of stuff does. So here, the warm air, it's pretty daggone cold up here right now in Minneapolis. So this is actually the tropopause. The top of the troposphere is right here, about 200 millibars. Now, if I looked at Brownsville, Texas, here's the top of the tropopause at about 110 millibars, way up higher. So the warm air has expanded down there, pushed the tropopause higher. So the troposphere is actually thicker in that area. So in the wintertime, the tropopause gets thinner, moves further down because the air is contracting because it's cold. So if you were down at the equator, though, it'd be all year long, it would be like this, very high up. So this is just another way we observe the atmosphere, putting it all together to make a forecast eventually we're going to talk about. So let me know if you have any questions about this.